In this video, I'm going to talk about some very general strategies for solving optimization problems that are application type, where you're given some kind of description in words of a scenario, and you have to figure out what you're maximizing or minimizing and how you're going to do it. So let me just give you a kind of outline of the strategy I would recommend. So the first step, obviously read through the problem, see if you can understand it. And one of my favorite approaches, or I think most powerful recommendations, would be to draw some sketches of the phenomenon that you're working on, or that you're trying to figure out how to optimize, and in particular include extreme cases. So in other words, if there's something that you're varying and something is changing as you vary that component, push it until the physical limitation in two directions, if that makes sense for the problem. Usually it should. And that will allow you to see some component of flexibility, like you get a real handle on what it is that is the slider that you're going to be looking for as a variable. So what element of the description is going to be your x, for example. So you include extremes, and then try and determine whether you anticipate whether the extreme you're looking for. Let's see. I should use the word extreme carefully here. What I mean by extremes here is, if you have, if your problem is you have a certain amount of fencing and you want to make an enclosure, then the extreme cases, this is sort of an in-between case, but if you have a limited amount of fence, you can put a tiny amount of fence on the vertical, and all of your, let's try to be a little bit more careful about that. So a tiny, tiny vertical element and a very long horizontal element to it. And so you're putting all of your fence into the horizontal and essentially zero. So that's like an extreme of your sort of distribution of the resource. And another extreme would be to have a very narrow and tall fenced off area like this. So those would be two extremes, and we would expect, if you're trying to maximize the area in an enclosure, the actual answer that you're looking for would be somewhere in between. So I should use the word extremes for these very sort of on the edge cases, and then to determine whether the optimum of interest is at the extremes, in which case you're going to find the largest value of the function at the endpoints of some interval or on the interior. And it's always useful to build as much of an expectation for what you think the answer could be. So if you think it's going to be on the interior, is it something where there's like a symmetric argument where you expect the middle of some interval to have the answer, to hold the optimum, or is there some reason to think that it's going to be somehow different? So the more expectation you can build before you even start, the easier it'll be to check that your answer in the end makes some sense. Okay, so the next step, and really you're starting to do this second step when you draw these pictures and try and figure out these extreme cases, but the next step is to determine the objective function, which is the thing you're maximizing or minimizing. And that might be a function of a single variable f of x, or it might be a function of two variables. And if it's a function of two variables, it's possible that there's some constraint that relates x and y to each other. Like in the case of the fence, you have, let's say, if x is one side and you have a certain amount of fencing, then you would have a constraint that says that 2 times x plus 2 times y would have to be 400. And now this relates x to y. So even if you have some objective function that's a function of x and y, you can use the constraint to reduce that down to a function of only x. However, if you're also including, for example, in our course, we have a section on multivariable functions, and you can actually optimize functions of two variables as well. But that's not the norm in a first term calculus course. So I would just assume that you generally would have a constraint relating x and y, if there is an x and y in your objective in the first place. Okay, so next thing would be to identify that constraint. And write down an expression for it. So, so the constraint, if you need it, would be, let's say, some function g of xy equal constant. So that's like the fencing example that I just wrote down, where we had 2x plus 2y is equal to the total amount of fencing that you can use. So this would be your g of xy, which would be different from your objective function. Let's say in that case of the fence around an enclosure, the f of xy would just be the area, which would be the height times the width of the enclosure. So you have one function for the objective function and another function for the constraint as part of the constraint. All right, so that's the third thing. So now that you have these, I would actually explicitly list here more sketching and try and translate your intuitive pictures into some kind of expression or some kind of intuition for what the function looks like, your objective function looks like. So more sketching, and then update your expectations. This is something that students generally underestimate, but it's a very powerful tool, especially in an exam where you don't have a lot of time. You want to have some simple way of checking that doesn't involve going back through all your work, and you want to just check it against some kind of intuition that you built at the beginning of the process. All right, so next step. Next step is to use the constraint to simplify your objective function. Oops. Simplify the objective. We're having spelling issues today, aren't we? So what I mean by that is use g of xy equals c, solve this for y, and then reduce your f of x to an f of x comma, let's say h of x, where we get an expression here, y equal h of x, as the solution of this constraint. Oh, it wouldn't be, well, it could be equal to 0, but let's say it's equal to some constant or some standard expression like that. Okay, and now once we have f, most likely you're going to have some limitations on x, so determine the domain for the problem. And don't get lulled into thinking that the domain of the function as written as a formula is going to give you the domain. The domain is going to be a combination of both the mathematical limitations on your objective function and also physical limitations in the problem. Like, for example, you don't want to have a negative amount of fence or something like that. Okay, so next step. So next I would go back, and now that you have a clear objective function, I would actually sketch those cases and sketch the extremes and an intermediate case, and make sure you see how those are going to translate into or translate out of the f objective function that you found. Okay, so so then you have to figure out, okay, if you're on a bounded closed domain, then there's a certain method that you would use. But if the problem is on an infinite domain, you have to think about maybe how you're going to justify any claims that you've found a maximum or minimum. Okay, so that could be on, let's say, a finite domain. You check the endpoints and you find all critical points, and that tells you that you have a maximum. If your domain is let's say from 0 to infinity, then you have to sort of come up with some idea of why. For example, if you your function starts at 0 and it goes positive and then it tapers off to 0 eventually, if you find that this is a critical point, maybe you find that it's even a local max. How do you justify the claim that it's a global max? You're not guaranteed, so you may just have to say a few words about how off at infinity it tapers off to 0. So you maybe want to say something about the limit of your objective function as x gets large or something like that. So, oops. So next thing, if you are on a finite domain, on a bounded and closed interval, find critical points and endpoints, and compare f values for those. So plug in your critical point, all your critical points into the objective function, plug in your endpoints, and pick the smallest or largest, depending on which you're looking for, mins or maxes. And the other option is, so this is sort of subcases really of 8. If the domain is open, or maybe unbounded, either one or both. That's a mess. Unbounded. Then you use some kind of global argument. By that I mean, so you found one critical point. So for example, one critical point, and the function is concave up. Everywhere. So that means that you have some critical point, a flat spot, and it's concave up on this side and concave up on that side forever. There's no way it can turn around. There's only one critical point, and so this must be the min. So this is the type of argument that you might have to come up with if you're not dealing with a bounded and closed interval like in option 9. Okay, so that's the general overall strategy. I will leave the video off here, and then I'll do another video with some examples where I kind of walk through each of these steps.